Hello, I'm Richard Lawson, and this is the first part of my talk about an introduction to radioactivity. Radioactivity is a natural phenomena that's been present in the Earth ever since it was formed 4,500 million years ago. But interestingly, it was only discovered relatively recently, about 125 years ago. Since then, it's been put to many useful applications, for example in nuclear power, generating electricity, by archaeologists for radiocarbon dating of finds. In the home, it's used in smoke detectors, and in medicine it's used for radioisotope therapy to treat patients, and in imaging to diagnose different conditions. Of course, we have to be aware of its dangers. It does cause genetic effects and cancer, so we have to use it with great caution and use it safely to make sure that the benefits outweigh any dangers. My particular interest is in nuclear medicine, which covers the areas of radioisotope therapy and radioisotope imaging. So in this talk I shall take my specific examples from that area which I'm familiar with, but I hope that this talk on an introduction to radioactivity will be of general interest to anyone who wants to know about radioactivity in any of its applications. In part 1 I'm going to talk about radioactive decay processes themselves. Then in part 2 I'll go on to talk about the interaction of radiation with matter, and in part 3 I'll talk specifically about the radionuclides that are used in nuclear medicine. So let's take a look at the fundamental particles that are some of the building blocks that make up matter. First of all, we have the proton, which has 1 unit of mass and a positive electric charge. I'm going to talk about mass in terms of units of electron volts, and I shall use this for both energy and mass because according to Einstein's equations E equals mc squared, energy and mass are equivalent, so I shall use the same units for both. I talk about electron volts, or keV, which is 1,000 electron volts, or meV, which is 1,000,000 electron volts. Now, the proton has a mass of 938 million electron volts, but you don't need to worry about remembering that. We just think of that as being 1 unit of mass. The neutron has also 1 unit of mass, only very slightly heavier than the proton, and it has no electric charge. It is neutral. The electron has a very small mass and a negative electric charge. In fact, its mass at 0.51 MeV is 2,000 times lighter than either the neutron or the proton, so compared with them its mass is negligible. The electron is often called the beta particle because historically that was what it was called before it was identified as an electron. So in this talk, whether I talk about electrons or beta particles, I'm referring to the same thing. The photon has no mass and no charge. The photon is the quantum that carries the electromagnetic radiation that we know as either light or radio waves or microwaves, X-rays or gamma rays. These are all examples of waves which are distinct from the protons, neutrons and electrons, which are particles. So those are the building blocks, the fundamental particles that I'll be talking about in this talk. Now, all matter is made up of atoms, and we used to think that atoms were indivisible, they couldn't be divided down any further, but nowadays we realise that atoms are made up of protons and neutrons and electrons. At the centre of each atom is the nucleus containing protons and neutrons, and surrounding it there is a cloud of electrons. And the electrons have a negative charge and the protons have a positive charge, and in a normal atom the number of electrons and protons are exactly equal, so their charges balance each other out, and overall the atom has 0 net charge. However, all the mass is at the centre because the protons and neutrons have significant mass, whereas the electrons have only a very small mass. This diagram gives the impression that the electrons go in orbits around the nucleus, rather like planets. It's perhaps not really quite like that. Think of it more just as a fuzzy cloud of electrons spread around the atom with the nucleus at the centre. Now, This diagram is rather misleading in terms of size, because the electron cloud is 10 to the minus 10 meters in size, which is very small, but the nucleus is 10,000 times smaller. So this really isn't to scale. If I was able to draw it to scale, you wouldn't be able to see the nucleus, which illustrates the fact that the atom is in fact mostly empty space. And I've got a little demonstration to illustrate that. Now, atoms are incredibly small. A single atom is far too small to be seen by the unaided human eye, and even with the best optical microscopes we can't see them. So it's very difficult to appreciate the size of an atom. But I like to use this balloon as a model. So if we were to take an atom and to blow it up 1,000 times, or 1,000,000 times, or 1,000 million times, we would end up something about the size of this balloon. So this balloon is a model representing an atom magnified 1,000 million times. In terms of size, it's quite good, but actually in one other respect it's not terribly much like an atom, because this balloon has got a well-defined shape and a hard edge, whereas an atom, the electron cloud around is very fuzzy. So maybe a model represented by a ball of cotton wool or a ball of candy floss might be more realistic. But in terms of its size, this is quite good, and it's good for one other respect as well. This represents the size of the atom in the cloud of electrons around the outside, but if we look inside to see how big the nucleus is, you see that little speck of dust just there? That to scale will be the size of the nucleus. So just like this balloon, an atom is mostly empty space, and the nucleus at the centre, although it comprises all of the mass, is a very small size. Now there I talked about the cloud of electrons having different possible orbits, different energy levels, and so we can draw a diagram like this showing the energy levels that the electrons can occupy, going up in energy from a lowest energy level here up to higher and higher levels. The number of electrons that you can have in each orbit is strictly limited. So for example, in the K shell we can only have 2 electrons, in the L shell we can have 8 electrons, and so on. So if an electron occupies all the lowest energy levels, which is what we call the ground state, the atom is in its ground state, it can't get down to any lower energy level. That means that the outer shell here has a few electrons and some vacancies for some more electrons. That determines how it can combine with other atoms. That determines the chemistry. So we call these the valence electrons. They are what determine the chemistry and how it can combine with other atoms. So in the ground state, all of the lowest shells are filled. But we can have radiation being absorbed by an atom. For example, radiation could come in and raise an electron up to a higher level. That's no longer in the ground state, that's in an excited state. Or if a little bit more energy is absorbed, it could knock an electron out altogether. That leaves it ionized. It becomes charged because it's lost one of its electrons. If we lose an inner electron here, for example, we've knocked out an electron from the K shell, leaving a vacancy here, then this electron from the L shell can come down to fill that vacancy, leaving a vacancy which can be filled by one from the M shell, and so on. And this cascade of electrons coming down gives off the energy in the form of a radiation that we would call X-rays. So that's what happens in the electrons in the energy levels surrounding the atom. But it's less well known that the same thing can happen in the nucleus. Now here it's a bit more complicated, because instead of just having one particle electrons, we've got 2. We've got protons and neutrons in the nucleus. So if we plot the energy up here, we have to have 2 diagrams, one here for the neutrons and one for the protons. And the rules here turn out that you can just have 2 protons or 2 neutrons in each of these energy levels. So you would imagine that to have a ground state you would have equal numbers of protons and neutrons, but it turns out that it's not quite that straightforward, because the protons are positively charged. So although the protons and neutrons are both held together strongly by something called the strong nuclear force when they're close to each other, because the protons have positive charge, they tend to repel each other, so they're not bound as tightly. So if you think of these energy levels as like a well with shelves in it that can be filled at different energy levels, the protons are not as tightly bound as the neutrons because of their repulsive positive charge. So this proton well doesn't go down quite as deep as the neutron well. That means when we have the lowest available energy state here, where the two are level at the top there, it turns out that although the number of neutrons and protons is roughly the same, there are going to be fewer protons than neutrons in this stable state. But we can also get a state where we have a neutron up here in a state with a vacancy down here in the proton energy levels. So it can decay to a more stable, a lower energy state by moving this neutron down into this proton level. That will happen by giving off energy in the form of a gamma ray. To do it though, it's got to turn a neutron into a proton, and that's the process that we call beta decay, or technically beta minus decay, and it happens if we've got too many neutrons compared with the number of protons. We can have the opposite, where we've got too many protons. So here we have a proton up here with a vacancy in the neutron energy level here. So if that proton decays down to here, it can give off the energy in the form of a gamma ray, but to do it, it has to turn a proton into a neutron, and that is the process that we call beta plus decay, the opposite of this beta minus. But we can also have something where we have an excited state, where we have a neutron up here at a high energy level with a vacancy down here, and it can move just down to the lower energy level, giving off the energy in the form of a gamma ray, but this time it doesn't have to change into a proton, so the number of protons and neutrons stays exactly the same. We call that an isomeric transition. So these changes in neutrons and protons in the nuclear energy levels are exactly equivalent to the same thing that you saw with electrons in the orbiting electron shells. So if we take an example of an atom like iodine, iodine has 53 electrons surrounding the nucleus, and in the nucleus we have 53 protons and 74 neutrons. So that means that the atomic number Z53 describes the chemistry of this. It's got 53 electrons. That describes how it will combine with other atoms, because it's the electrons that do that, and that's balanced by 53 protons in the nucleus. So 53, the number of protons and neutrons, is its atomic number. But the mass consists of 53 protons and 74 neutrons, and we can ignore the electrons because they're so light. So the total mass is 53 plus 74, which is 127. So we can write this as iodine 127 and with a subscript 53. The 53 is the atomic number, I is the chemical symbol. Now actually those always go together, because if it has 53 protons, that means the chemistry is of that of iodine, because that's what happens with the 53 protons, which match 53 electrons. So if it's 53, it has to be iodine. So we often miss out the 53, writing the iodine is sufficient. But the 127 here, the total mass, means we can say that it must have 74 neutrons to make up the total mass of 127. So we write iodine 127. That is normal, stable, non-radioactive iodine, the sort of thing that you could get in a jar from the chemists. But we can plot something that we call a chart of the nuclides, which shows all of the possible combinations of protons and neutrons. So this chart of the nuclides has the number of protons, which I call Z up here, and the number of neutrons, which we call N, across here. So each square on this chart represents a different combination of Z protons and N neutrons. And as I said, the mass A is the sum of neutrons and protons, so as we go up here the mass A increases. As I said, a stable atom has roughly an equal number of protons and neutrons, but it tends to have slightly more neutrons and protons. So these black squares here, which are the stable ones, follow a line at approximately 45 degrees, but it curves over towards the neutron side because we have slightly more neutrons and protons to make it stable. So the black squares are the stable nuclides, the stable combinations of protons and neutrons. The red squares above the line of stability are the ones that are not stable because they've got too many protons, and the ones below the line of stability in blue here are not stable because they've got too many neutrons. There are some at the top here shown in yellow and green which are not stable just because they're too heavy. I'll talk about those in a moment. As far as radioactivity is concerned, the black squares, the stable ones, aren't of interest. It's the radioactive ones that are of interest because we can detect the radiation that they give off. So let's just make clear some definitions. When I use the word nuclide, I mean a particular combination of Z and N, a given square on this chart. Each square on that chart represents a different combination of protons Z and neutrons N, and so each square is a different nuclide. The radionuclides are the interesting ones, the radioactive ones, the red and the blue ones, the coloured squares. Isotopes has a slightly different meaning. It means the same number of protons. So nuclides with the same Z but different N have the same number of protons but different number of neutrons. So everything on one row across this chart is an isotope. It has the same number of protons. So because they have the same number of protons, they have the same chemistry, they combine in the same way, they're all chemically identical. The radioisotopes are the radioactive isotopes, so those are the coloured squares on the same row, and those are the ones that we're interested in. So let's look at an expanded view of a bit of that chart that corresponds to the isotopes of iodine. Iodine has atomic number 53, so this row Z equals 53 corresponds to all of the isotopes of iodine, and you'll see that there's one black square on that row, so there's one stable isotope of iodine, although some of the other elements above and below have more than one black square. They have more stable isotopes. But if we look at the black square here, we see that that corresponds to 74 neutrons, which together with the 53 protons makes a total mass of 127. So we write that as iodine 127, and it's a black square, so it's stable. But if we look at this red square here, it has only got 70 neutrons compared with the 74 that it needs to be stable. So it's got too few neutrons or too many protons compared with the stable version. So this iodine 123 is radioactive. The blue square here, on the other hand, has got more neutrons. It's got 78 neutrons compared with the 74 that made it stable. So the total mass of 78 neutrons and 53 protons makes a mass of 131, which is iodine 131, and that's radioactive because it's got too many neutrons. But crucially, all of these are chemically identical. They all behave the same chemically, but because some of them are radioactive, we can make use of them, for example, to follow where they go in particular reactions. So I'm going to describe a few different radioactive decay processes. I'm going to describe what happens if we have too many protons, in which case we can have electron capture or positron emission, which is also known as beta plus decay. If we have too many neutrons, we can have electron emission, which is technically known as beta minus decay. Often it's just called beta decay because the original form of beta decay was beta minus. So if we say beta decay, we generally mean beta minus decay. Beta plus decay is often just referred to as positron emission. It can be that we just have too much energy, in which case we have isomeric transition, or we just have things that are too heavy, in which case we can have alpha decay or fission, and I'm going to describe each of those processes in turn. So if we start with electron capture decay, this happens when we have too many protons. So if we look at the nucleus here, we find that it can capture one of its own orbiting electrons, and the electron that's captured combines with the proton. They each have opposite charge, so we end up with a neutron which has no charge. So the proton capturing an electron turns into a neutron. That means that we've changed the atom. We've rearranged the protons and neutrons in the nucleus, and the excess energy comes off as a gamma ray in the process of gamma emission. But we've by converting a proton into a neutron, we've now got an optimum number of protons, so this has become stable. We could describe it as saying that the nucleus with an excess of protons has captured an atomic electron to form a stable nucleus and given off the gamma ray by the proton changing into a neutron. In the energy level diagram that I showed you, it corresponds to this situation here, when we have a proton at a higher energy level here and a vacancy for a neutron at a lower energy level. So by moving down here, the proton changes into a neutron and gives off the gamma ray. So that's the process of electron capture decay. Here is an example of a radionuclide that decays by electron capture decay. Iodine 123 decays by absorbing one of its own atomic electrons, and it turns into tellurium 123, and it does so with a half-life of 13 hours. I'll talk about half-life shortly. See, what we've done is we started off with 53 protons and turned a proton into a neutron, so we've ended up with 52 protons. So 53 was iodine, element 52 is tellurium. We have changed the iodine into tellurium, but the total mass, which is protons plus neutrons together, it still remains at 123. The excess energy comes off as this gamma ray of 159 keV. And we can look at the decay scheme in this diagram here, where we plot the atomic number across here, increasing number of protons further to the right, and the energy up here. So each of these levels here represents a state within the nucleus with increasing energy. We start off at the top here with a high energy state, which is the iodine 123, which has got the half-life of 13 hours. It decays by electron capture by reducing the energy and also reducing the number of protons. So we move across to the left in the diagram, and we end up at this energy level here, which has got an energy of 159 keV above the ground state, and that immediately decays down into the ground state, giving off the energy in the form of this gamma ray with 159 keV of energy, and we end up with tellurium 123, which is stable. So that decay scheme allows us to understand the decay and see what emissions it gives. Notice that this is a nice emission. It gives a gamma ray but no beta particles. However, because we started by absorbing one of its own atomic electrons, and of its necessity we will end up with a vacancy in one of the inner electron shells, which means we'll get characteristic X-rays following that as the electrons from higher shells cascade down. So this decay doesn't give any beta particles, but it does give some characteristic X-rays as well as the gamma rays. On the chart of the nuclides, it looks like this. This was the square here. This is iodine 123, and it decayed here by turning a proton into a neutron. So we come down in protons and increase in neutrons. So we come down and to the right, turning it into tellurium 123. So that's what happens with electron capture decay, and we see we started with a radioactive red square, but we've ended up in a black, a stable square, so we've ended up with a stable atom after that decay. The next process I want to talk about is positron emission, also known as beta plus decay. This is an alternative to electron capture if you have too many protons. So here's an example of another nucleus with too many protons. Instead of capturing one of its own orbiting electrons, what it can do is to emit a positive electron. That's what we call a positron. It's the antiparticle of an electron. Because the electron is often called the beta particle, the positron is sometimes called a beta plus. So you see we had a proton in the nucleus which turned into a neutron and gave off this positron. So we now end up with the optimum number of protons again, and the excess energy comes off as this gamma ray. So a nucleus with too many protons turns into a stable nucleus with this emitted positron and the energy coming off as a gamma ray by the proton turning into a neutron. On my energy level diagram, it was like this one again. A proton here turns into a neutron, giving off its excess energy. So that was an alternative to electron capture. An example of an atom that decays by positron decay is iodine-124. It has a half-life of 4 days and it turns into tellurium-124. Because once again we started with 53 protons, we turned a proton into a neutron, so we end up with 52 protons, and that is tellurium. The positive charge is balanced by emitting this positive electron, a positron, and the excess energy comes off as the gamma ray, which has 603 keV of energy. On the decay scheme, we start off with iodine-124 at a high energy here with a 4-day half-life, and in 13% of the cases it will emit this positron with a maximum energy of 1440 keV, bringing it down in energy and to the left because we have reduced the number of protons, and it ends up at this state here, which is 603 keV above the ground state. So it gives off the energy as this gamma ray here with 603 keV, becoming stable iodine tellurium-124. In 13% of the case, it may go straight down to this ground state, giving off a positron with an energy of 2150 keV, and in that case you don't get any gamma rays. This is a simplified decay scheme because those don't add up to 100%. There are other possible decays as well. So in that case we got one of several different positrons, beta plus particles. The energy I've shown here is the maximum energy. In fact, they have a range of energies from 0 up to that maximum, because there are also particles called neutrinos, which I didn't mention, which take off some of the energy as well. So on the chart of the nuclides, we started off with this square here, which is iodine-124, and we lost a proton, so it came down, gained a neutron, so it moved to the right, and we end up with this black square here, which is tellurium-124. If we have too many neutrons, the only form of decay possible is electron emission, also known as beta minus decay. In the process of electron emission, we have a nucleus with too many neutrons. So if it emits an electron with a negative charge, that will turn the neutron into a proton. That means we end up with the correct number of neutrons, but the excess energy comes off as a gamma ray in gamma emission. So the electron, as I said, is also known as a beta particle, and we start with a nucleus with too many neutrons, and by turning a neutron into a proton we end up with a stable nucleus, and the emitted electron is the beta particle, and the energy comes off as a gamma ray. And on my diagram of energy levels in the nucleus, you see we have here a neutron at a high level with a vacancy here for a proton at a lower level, and by that neutron turning into a proton we can give off the excess energy as a gamma ray, and the whole thing becomes more stable. An example of a nuclide that decays by beta minus decay is iodine-131. We have iodine-131, which decays with a half-life of 8 days, into xenon-131. So here we have converted a neutron into a proton, so we have gone up from 53 protons, which was iodine, to 54 protons, which is xenon. But the total mass, the number of protons plus neutrons, has not changed from 131, so that's why we end up with xenon-131. The beta particle that is emitted, which is an electron, balances the charges, and we get one of several gamma rays to take off the excess energy. And if we look at the decay scheme, we can see here the iodine 131 with an 8-day half-life is this high energy level here, and in 80% of cases it can give off this beta particle here, which has a maximum energy of 606 keV, which comes down to this energy level here and is immediately followed by a gamma ray which is emitted with that 364 keV energy. In 7% of cases we get a different beta particle with a different gamma ray, in this case an energy of 637 keV. So we get several different gamma rays and beta particles. The energy of the beta particles that I've quoted here is the maximum. That's because some of the energy is taken off by neutrinos, so the beta particles have a range of energies from 0 up to that maximum. If we look at the chart of the nuclides, you see we started here with iodine 131, which is this blue square here, and we lost a neutron and gained a proton, so we moved left and up, and that ends up with this black square here, which is xenon 131, which is stable. We can also have something where we've got the right number of protons and neutrons, but they just have too much energy, and in that case we have what we call isomeric transition. So in isomeric transition, all we have to do is to rearrange the protons and neutrons and give off the excess energy. So we start with a nucleus with too much energy, simply adjust the nuclear energy levels to end up with a stable nucleus and a gamma ray. And in my chart, my diagram here, we have an excited state here and a neutron in a higher energy level. We can just decay down to fill that vacancy there without needing to change the number of neutrons or protons at all. That's why it's called isomeric. It doesn't change the number of neutrons or protons. So in an isomeric transition, there is no change in the number of protons or neutrons. So Z and N remain the same. So it remains the same nuclide. It doesn't change at all. So it's just a change in the configuration of the protons and neutrons in the nucleus that result in a more stable configuration. And it releases the energy as pure gamma emission. So this is a very nice clean form of decay. We just get gamma rays, we don't get any beta particles at all. This is particularly important for things that we call metastable states. That's something where the energy level has an unusually long lifetime. In most of the decays that I've been talking about, where we get a beta emission followed by gamma emission, the gamma emission follows immediately after the beta decay. If we have a state where it lasts for an unusually long time before the gamma emission, then that's what we call this metastable state. It lives for an unusually long time. So here's an example of a metastable state. It occurs in the beta decay of molybdenum-99. That has a half-life of 67 hours, and it decays by emitting a beta particle and some gamma rays down to technetium-99. But there's in 80% of decays it gives off this beta particle, which ends up in a state here which doesn't decay immediately by emitting a gamma ray. Instead it stays there for a long time with a half-life of 6 hours. So this is an example of what we call a metastable state. We give it the symbol 99M, the M meaning metastable. In fact, because it lasts long enough, we can separate that out from the decay of the molybdenum and look at that as if it was a separate entity in itself. So we can write the decay scheme for technetium-99M, which decays by isomeric transition from this energy level here at 140 keV. In 88% of cases it gives off this gamma ray of 140 keV and ends up at technetium-99. So overall we can write that technetium-99M, with the M for metastable, with a half-life of 6 hours, decays into technetium-99 without the M, and in doing so gives off a 140 keV gamma ray. Once again, that's a nice pure form of emission, and that's very important in nuclear medicine. Actually, the ground state here of technetium-99 is not completely stable. It's got a very long half-life of 200,000 years, but in human terms that's long enough for us not to have to worry about it, at least not for nuclear medicine purposes. Then finally we can think what happens if we have something that's too heavy, when we can have alpha decay or fission. So a heavy nuclide may lose some mass by ejecting an alpha particle. Now an alpha particle is 2 protons and 2 neutrons, so it's got a mass of 4 units, so it can lose quite a bit of mass in doing that. In losing 2 protons and 2 neutrons, it comes down and to the left by 2 squares, so it will come back down towards the stable area by losing that alpha particle. And the 2 protons and 2 neutrons are very nicely stable, bound together. That alpha particle, which is actually the nucleus of a helium atom, is a nice stable particle to be emitted. Alternatively, if we have very heavy nuclides, another thing that can happen is that they can split into 2. This is the process of fission, where we get a nuclide at the top here that splits into 2 different nuclides partway down the chart. And the excess energy is getting carried off by gamma rays, but we usually end up with 1 or 2 spare neutrons as well, which can induce fission in other nuclide and in other atoms. So this is the process of fission, which is made use of in nuclear power and also as a way of producing other radionuclides. Now people often ask, what's the difference between gamma rays and X-rays? I've talked about both in this talk. People sometimes think that the gamma rays will have higher energy than X-rays, but that's not really true. They are both forms of high energy electromagnetic waves, and although gamma rays can have higher energy than X-rays, for example 100 kV is a typical energy for both an X-ray and a gamma ray. You wouldn't distinguish between them. There is no difference between X-rays and gamma rays. It's purely a matter of naming. X-rays were named when they came from electrons, a rearrangement of electrons in the atom. The energy level diagrams that I showed you at the start for the energy levels of electrons orbiting the atom, where they transition between energies there, we gave off monoenergetic X-rays. We also have X-rays from X-ray tubes when we stop a beam of electrons in a hunk of metal, and that gives a broad spread of energies, but both of those are what we call X-rays, whereas gamma rays originate, as I've been talking about, from rearrangement of protons and neutrons in the nucleus. Those are also monoenergetic. We can also get gamma rays when electrons and positrons annihilate. Those are 511 kV gamma rays I'll talk about a little bit later. So it's purely a matter of naming. There are no difference in the properties of X-rays and gamma rays. The naming is purely historical of where they actually come from. Now I need to talk about the units that we use for radioactivity. The amount of radioactivity of a source is measured by the number of atoms that decay in a given time, how many decays happen per second. And 1 disintegration per second is given the special name of the becquerel, after Henri Becquerel, the Frenchman who discovered radioactivity in 1896. So 1 becquerel, 1 disintegration per second, is a very, very small amount of activity. So we usually talk about millions of disintegrations a second, which is a megabecquerel, or 1,000 million disintegrations a second, which is a gigabecquerel. However, if some of the atoms are decaying all the time, then there must be fewer left to decay later on. So as time goes on, there are fewer and fewer atoms left, so the number available to decay falls with time. That means that the activity must fall with time. So because the atoms are decaying, it's true that the activity must also fall with time. So let's consider a simple example of radioactive decay where we start with 100 radioactive atoms. I know that's not very many, but this is just a simple illustration. So how many will be left if you lose 10 atoms every second? Well, you start with 100. Clearly after 1 second you've lost 10, so you've got 90, and then 80, and then 70. So the activity would fall linearly with time, and it would eventually fall to no atoms left after 10 seconds. But suppose it's different. Supposing instead of losing 10 atoms every second, you lose 10% every second. Well, in the first second, you'd lose 10% of 100, which is 10, so you'd have 90. In the next second, you'd lose 10% of 90, which is 9, so you'd have 81, and then you'd lose 10% of that, and so on. So you see that in this case, you don't get a linear fall, you get the yellow curve, which is what we call an exponential curve. The rate of fall gets less and less as there are fewer atoms left, so it never quite reaches zero. In fact, we can talk about the time it takes to halve. If it had been the linear fall, the purple line would have fallen to half after 5 seconds, but the exponential yellow curve here takes longer. It takes 7 seconds to halve. So let's talk about the activity and half-life. Radioactive decay is like that. It results in a fixed percentage of atoms decaying every second. So the fall is exponential, not the linear one that you might expect. So the rate of fall gets less with time. We get a curve like this that falls slower and slower as time goes on and never quite reaches zero. It tends towards it. So we measure the fall by the half-life, which we can call T a half. That is the time taken for activity to halve. Mathematically, we can write that the activity at time t is the activity at time 0, this activity here, multiplied by E, which is a constant, to the power of minus 0.693 times t over t a half, where t is the time now and t is this half time. So if t is equal to t a half, then that is 1, so this is e to the minus 0.693. And if you plug that into a calculator, you'll see that e to the minus 0.693 is exactly a half. So this becomes at is a0 times a half. In other words, when t is equal to t a half, here on the graph, the activity is a half a0. It has fallen to half of what it was. So that's what we mean by the half time. It's fallen from a0 to a half a0 in a time equal to t a half. And in fact, when t is equal to 2 t a half, here it's fallen to a quarter of a0. You get that by putting that into the equation, or by saying, well, it started off here at a half a0, and after another half-life it will halve again to a quarter, and clearly after 3 half-lives it halves again. Here it halved to an eighth, and so on. So that's what we mean by half-life, the time it takes for the activity to fall by a half. So to summarise what I've said in this part, here we can see that we discussed the red squares, which were too many protons, which decay either by electron capture decay or positron decay. The blue squares, which had too many neutrons, decayed by beta decay. We had the green squares at the top, which were too heavy, that decayed by alpha decay or fission. And we had those which just had too much energy, which decayed by isomeric transition. So that's the end of part 1 of this talk. In the second part, I will describe how radiation interacts with matter.